Hey, welcome back. Here we are at data analysis for the humanities, and we are doing some Python, and we're discussing functions, and we're discussing chaotic functions. And last time we talked about the logistic map, which is a very simple function. The new x at any step in a series is the previous x multiplied with a constant r multiplied with 1 minus x. And this gives you a whole range of interesting behaviors, and you should go back to the previous video to see it if you are not sure, if you don't remember it, that range from a totally boring function to a function that converges to a particular limit, and then to a function that seems to be truly random, like what you see here on the screen. So how can we interpret this in a way that makes sense? What is this function actually modeling? And for this you have to remember, here is this function, you have to remember that the whole thing started as a biological simulation. There was a man called Robert May in around 1975, and he wanted to model populations of organisms, let's say of bacteria, that live in a resource restricted environment, which is the normal case for biology, right? You have bacteria in a dish, and the dish is limited. You have humans on Earth, and the Earth and its resources are limited. You have animals, let's say rabbits, in a field with lettuce and carrots, but the amount of lettuce and carrots is limited. So if you fence the rabbits in, at some point the population will reach a maximum value. And why will this happen? Because the rabbits will eat all the lettuce, they will eat all the carrots, they will have nothing to eat, and they will die. Then you have 0 rabbits. But will this happen? And how do I know what will really happen? And this is what May was trying to research. And what he did was first to make this formula. So let's briefly talk about how this formula works. You have x at the time n plus 1. So you divide time in this discrete time steps. Let's say you look every day. And at the day plus 1, you have a situation that is described by x to the time n, so the previous day, multiplied by r, where r is some kind of reproduction rate that is normalized over this whole population. So it's not an individual's reproduction rate, but it is how the system grows. It's a kind of growth rate for the system. So the system grows over time, right? So you have r is the growth rate multiplied with the number of individuals, gives you the new number of individuals, right? Makes sense so far. And this would just be a thing that grows forever. If you had growth like this, where you have the numbers of individuals and they reproduce, each one splits, let's say, into 2 or 3 or 4 individuals, then you would have an exponential growth like this. You have the reproduction rate multiplied with the number of individuals. But now May said, okay, that's not true for biological systems, because I also have this other factor, 1 minus x. And this represents my environmental limits. These are the resources I have. And the more x I have, the fewer resources I have. So originally, my environment has resources 1. Remember, it's normalized to 0 from 0 to 1. So my amount of resources is 1. And if the environment is empty, my population is 0. And now, as my population grows, they eat away the resources proportionally to the population. So if I have 0.8 population, then I only have 0.2 of resources left. And so my resources are 1, the maximum resources for the environment, minus x. And now I multiply this also into my formula. So the population is not only growing because of this reproduction rate, it is also limited by the availability of resources. And the more it grows, the fewer resources it has. And multiplying this in here means that it cannot grow anymore. At some point, the restriction in resources will make my population shrink. And if I execute it again now, you see the pattern of before, and you can see it better if you first use a smaller number of R. Let's take something more benign here, 2.9, and then you see that now I get this curve, this logistic map for the rabbits in a closed room with lettuces and carrots that reproduce by seeding, and I leave them long enough and the rabbits don't reproduce very much, and so you see that it reaches an equilibrium. At some point, if there were too many rabbits, they died off. If there were too few of them, they reproduced, so that in the end I reach an optimal number of rabbits that is sustained over time, because now I have as many rabbits as my lettuces and carrots will be able to sustain. And so these rabbits eat these carrots and these lettuces and they stay alive. If they reproduce more than they should, their offspring dies because there's not enough food. If they reproduce less, they will have additional food, which will allow them then to reproduce more and again reach this equilibrium state. Now, if my growth rate is very high, something bad happens. Let's make my growth rate be 3.4. Now I have this kind of behavior. Again, it's regular. You see that things stabilize, but they stabilize in a pretty wild way. Now my rabbits are not stabilizing at one number where I have 50 happy rabbits in my room, but now I have a population that's exploding and crashing relatively regularly. So the values are more or less the same over here, but from one generation to the next, the population is always swinging back and forth, because my reproduction rate is so high that when even 2 rabbits more in one generation can survive, these will produce 100 rabbits in the next generation. So that suddenly I have hundreds of rabbits more, and this is too much for the room, and it must crash. And so most of these rabbits die, all of them, almost. 2 or 3 remain. And these now have such a huge reproduction rate again, that now that there are only 2 or 3, they can freely reproduce again. So again, they produce hundreds of rabbits, which immediately crash. And then you get this wild oscillation here. And so on. And then you have at some point, when you go to 3.9, you have such a high reproduction rate that now you have this chaotic behavior where the number of rabbits is not predictable anymore. You will get some number of rabbits that you cannot tell what it will be until you actually measure them. Yeah, that's it. That's the biological interpretation of the logistic map function. And this is what this person here we call, here's the description in the lecture notes, this person, Robert May, found about it in 1975. And this is a very interesting relationship because it applies to so many things. It's not only reproduction of rabbits, it is every process of growth under restricted resources. You can use it to simulate population growth of humans, bacterial growth in food, all kinds of things where something grows in an environment that is restricted. Again, if you don't like the graphics, I gave you some of the values here in tables of values. You can look at them. You can see how the numbers develop, and you can do your own experiments. You can change values in the program to try to see what will happen. One last thing, if you are looking at this code and you wonder why we throw away some iterations, which we do here at some point, it says keep only the last iterations. The point here is that all these systems reach their typical behavior, or most of the systems. Okay, this doesn't have a typical behavior because it's random, but if you have a typical behavior, this behavior is only reached after some time. So here the typical behavior is to stay under 0.475, but this is not immediately reached. We start with up here and we first have to fall down. If I make it a little bigger, at 2.9, I have this behavior. Again, the final point of equilibrium is reached only after the 40th, 50th iteration. Before 50 iterations, it's diminishing, it's oscillating with a diminishing amplitude, but it has not yet reached its equilibrium, right? And so we don't want to see in our plots these initial movements that the system needs in order to stabilize. We want to see what's the stable condition of the system. And so this is why we throw away the first 50, 100 iterations, how much it is, so that we get only the part of the function where it's stabilized. Of course, if it's not stable, like in the chaotic situation, it doesn't make a difference, right? I could take all of them, or I can take the last. It's the same because there is no pattern. So yeah, this is what we do here, why this is the case that we throw away the beginning. And now the last thing that we need to see is that we can plot it in a particular way, which is very interesting, which gives us this. And this is the so-called bifurcation diagram of the logistic map. This is not difficult to understand. It looks a little surprising, but you will easily see what it means. Here I have the growth rate on the right. This is my R factor, right? My reproduction rate, which I can make bigger or smaller. With a reproduction rate of 2.6, my system stabilizes over time. So this is the point at which the system stabilizes over time. This is after 1,000 iterations, let's say. So in this diagram, you don't see one iteration. You see 1,000 iterations for every point. So after 1,000 iterations with a growth rate of 2.6, the system stabilizes on 0.6. If I increase my growth rate, the value at which we stabilize grows a little bit, but doesn't fundamentally change. But after 3, here, 3.1 somewhere, something happens. The system splits. It bifurcates, as we say, which comes from fork, because it forks, and bi means two, right? So it bifurcates, it splits into two. And this is what we saw before. When I have these values of 3.1 or something, I get two stable points, a low point and a high point, and the system oscillates between them. And then is another bifurcation point after around 3.5, where it splits again. And now I have these 4 points, you remember, 2 high, 2 low points, and the system jumps between them. And then I have another split here, which is 8 and 16 and 32. And then I get all these random, more or less, endless number of points where the system jumps between them in every iteration, unpredictably. But what's interesting is that I also get these islands of order. So there is a value around 3.8, 3.9, at which, here's 3.9, between 3.8 and 3.9, 3.83, at which actually the system again reaches an equilibrium, at which I will have only one value at which the rabbit population stabilizes until it bifurcates again here and starts splitting again. This is interesting to think about what happens there. Why does this system now stabilize? If you think about it in terms of rabbits, it's not clear anymore, right? What happens? Why is there this regularity? And I'm not a mathematician. I don't know if mathematicians actually know why this happens or what this means, how to interpret this. But it's interesting that the chaotic behavior is not totally chaotic. It's chaotic, but it is interrupted by islands of order like this again. Yeah, that's all we wanted to talk about. So you have these different functions. You have linear, you have nonlinear functions, you have totally random processes, and then you have chaotic processes which exhibit this transition behavior from ordered to disordered, from order to randomness to chaos. And this is often only a single parameter that changes, that makes the behavior of the system change completely from an ordered system to a chaotic system. So next time we will talk a little more about mathematics, because in order to understand data analysis and particularly machine learning, we need to at least understand qualitatively what a derivative is, what the slope of a function is at a particular point. And we won't need the mathematics of it, at least not the full mathematics of it, but we need to understand the principle of it. So come back next time and I will try to explain to you what derivatives are, in case you have forgotten. If you already know what they are, you're wrong for here. You shouldn't be watching these videos. Thank you and see you next time. Bye-bye.